Hello everyone, today we'll study mathematical expectation. Mathematical expectation of a random variable. Mathematical expectation is also called the expected value. Mathematical expectation is also called the expected value. First of all, let me introduce what is a mathematical expectation. Let x be a random variable. It may be continuous, may be discrete. Let x be a random variable with probability function or probability density function f of x. Let x be a random variable with probability function or probability density function f of x. Its mathematical expectation. Its mathematical expectation is defined as E of x its mathematical expectation is defined as E of x that equal to the sum of all x in the support x times f of x if s is discrete. If s is discrete, its expectation E of x, this is capital X. Its expectation, mathematical expectation E of x is the sum of all x in the support of x times f of x. That's its mathematical expectation, or it's called expected value. Or E of x equal to the integral from net infinity to infinity x times f of x dx. If x is continuous, if x is a continuous random variable. So if s is a discrete random variable, its expectation is E of x equal to the sum of all x in the support of x times f of x. If s is a continuous random variable, its mathematical expectation is integral from net infinity to infinity x times f of x dx. Note, in general, we use Greek letter mu. In general, we use Greek letter mu. In general, we use Greek letter mu to represent the expected value. So mu equal to E of x. So in general, we say mu equal to E of x. This x is a capital letter. This x is a random variable. This is a capital letter X. So mu equal to expected value of x. Next, before I explain what does mathematical expectation mean, let me first of all show you some computation. Then I'll explain what does it means. Look at this example here. When rolling a die, let the random variable x represent the outcome of the die. Find the expected value of x, which means the mathematical expectation of x. Mathematical expectation of x. So first step, let's recognize what kind of probability distribution x is. What kind of probability distribution x is? Here, x represents the outcome of a die. The outcome of a die is 1, 2, 3, 4, 5, 6. And we know that every number has the same chance to come up. Every number has the same chance to come up. So this is a uniform distribution. This is a discrete uniform distribution. So x has a discrete uniform distribution. X has a discrete uniform distribution. It's uniform over the set from number 1, 2, 3, 4, 5, 6, from number 1 to 6. X has a uniform distribution over the set with elements 1, 2, 3, 4, 5, 6. Next, let's find its probability function. For discrete uniform distribution, probability function is 1 over n, where n is the size of the set, n is the cardinality of the set. Here in the set, there are 6 elements. So n is 6 here. Here s could be 1, 2, 3, 4, 5, 6. Next, find support. Support represents a set of all possible outcomes that S could be. When we roll a die, S could be 1, 2, 3, 4, 5, 6. The outcome could be 1, 2, 3, 4, 5, 6. So support of X is 1, 2, 3, 4, 5, 6. So that's the setup of the problem. That's the setup. Now, based on the setup, find the expected value of X. This X is a discrete random variable. So its expectation is the sum of all X in the support. The sum of all X in the support. X times f of X. For the sum of all X in the support, X is 1, 2, 3, 4, 5, 6. So X is from 1 to 6. X is from 1 to 6. X times f of X. So X value is from 1 to 6. When S is 1, I have 1 times f of 1. When S is 2, I have 2 times f of 2. When S is 3, I have 3 times f of 3. When S is 4, I have 4 times f of 4. Then 5 times f of 5. And 6 times f of 6. We know that f of 1. F of S is a constant function. No matter what I plug in, I always get 1 over 6. F of 2 is also 1 over 6. F of 3 is also 1 over 6. F of 4 is also 1 over 6. F of 5 is 1 over 6. F of 6 is 1 over 6. Together, if I multiply, I have 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is 21. 21 times 1 over 6 is 21 over 6, which is 3.5. Now, what does this number 3.5 mean? This number 3.5 is the mathematical expectation of X. What does it mean? Let me give you some rough idea. Think of this way. When we roll a die, every time we obtain a number from number 1 through number 6. If we roll a die multiple times and write down the result every time, we obtain a sequence of numbers where each number is between number 1 and number 6. For example, when we roll a die, if I roll a die, I get 2, I write down 2. Roll a die again, if I get 5, write down 5. Roll a die again, if I get 1, write down 1. Roll a die again, if I get 3, write down 3. Roll a die again, if I get 5, write down 5. Roll a die again, if I get 6, write down 6. Roll a die again, if I get 4, write down 4. Roll a die again, if I get 3, write down 3. Roll a die again, if I get 5, write down 5. Roll a die again, if I get 1, write down 1. And keep going. If we keep rolling the die, we will obtain a sequence of numbers where each number is between 1 and 6. If we roll a die a large number of times, if we roll a die a large amount of times, we will obtain a very, very long sequence of numbers between number 1 and number 6. If we roll a die a large amount of times, we will have a very, very long sequence where each number is between number 1 and number 6. Now, if I add all these numbers together, and find an average, the average will be very, very close to 3.5, which is the expected value of x. So, a rough idea about expected value is that the expected value represent what we expect to get on average in the long run. Represent what we expect to get on average in the long run. So the expected value represents what we expect to get on average in the long run. That is some rough idea about expected value. Here, the random variable x represents the outcome of the die. If we repeat the experiment over and over a large amount of times, expected value of x represents the average of the outcome in the long run. In this example, if we roll a die a large amount of times, we expect to get 3.5. We expect to get 3.5 as an average of all outcomes together. We expect to get 3.5 as an average of all outcomes together. Next example, then the probability function of a random variable x be f of x, where f of x is 1 over 6 if s is 2, 1 over 3 if s is 4, 1 over 2 if s is 6, 0 otherwise. Find the expected value of x. First step, let's try to find the support of x first. First step, let's find the support of x first. What's the support of x here? The set of all possible values of x is 2, 4, and 6. Here, support of x is the set of number 2, number 4, and number 6. Find support of x first. Based on the support, we can see that this random variable x is a discrete random variable. So the expected value for discrete random variable is the sum of all x in the support, x times f of x. The sum of all x in the support. In the support, we have x equal to 2, 4, and 6. So we have 2 times f of 2 plus 4 times f of 4 plus 6 times f of 6. Then f of 2, where s is 2, f of x is 1 over 6. f of 2 is 1 over 6. F of 4, where s is 4, f of x is 1/3. For f of 6, if s is 6, f of x is half. Together, 2 times 1, 6, 4 times 1/3, 6 times half. That's 1/3 plus 4/3 plus 3. 3 can be rewritten as 3 over 1. Then we have 3 on the denominator. 1 plus 4 plus 9 is 14. So the expected value of x is 14 over 3. Next, let the probability density function of a random variable x be f of x, where f of x equal to 3x squared if s is between 0 and 1, and 0 otherwise. Find expected value of x. So first step, let's find support of x first. In order to find expected value, let's find support of x first. Here, support of x is the interval from 0 to 1. And for the support, usually we use closed interval. For the support, it doesn't matter it's closed or open. For support, we write closed interval from 0 to 1. That's support of x. Since support of x is an interval, we know that this random variable x is a continuous random variable. Since the support of x is an interval, we know that this random variable x is a continuous random variable. So for continuous random variable, the expected value is integral from net infinity to infinity x times f of x dx. Since x is a continuous random variable, expected value of x is integral from net infinity to infinity x times f of x dx. And then we know that support of x is from 0 to 1. Support of x is from 0 to 1. So take integral from 0 to 1 x times f of x. When s is between 0 and 1, f of x, the PDF f of x is 3x squared. Then simplify, we get integral from 0 to 1, 3x cubed dx. Then take antiderivative, that's 3 times x to the power 4 over 4. Evaluate from 0 to 1. If we plug in 1 for x, we get 3 over 4. If I plug in 0 for x, we get 0. Answer is 3 over 4. That's the expected value of x. Next example, let x be the random variable with x has a binomial distribution with n equal to 4 and p equal to 1/3. Find expected value of x. So if we don't know the probability function, let's find probability function first. Here x is a binomial distribution where n equal to 4, p equal to 3. The probability function for binomial distribution is f of x equal to n choose x, p to the power of x, times 1 minus p to the power of n minus x. If we plug in n and p, what do we get? If we plug in n and p, n is 4, p is 1/3, we have 4 choose x times 1/3 to the power of x. 1 minus 1/3 is 2/3 to the power of m minus x. n is 4, so you get 4 minus x. That's the probability function of x. Next, find the support. Find support of x. Next, find support of x. Since x has a binomial distribution, support of x is a set of all integers from 0 to n. Support of x is integers from 0 to n. Here is from 0, 1, 2, 3 to 4. For binomial distribution, support is from 0 to n. Integers from 0 to n. Here we have 0, 1, 2, 3, and 4. Next, find f of 0, 1, 2, 3, 4. Find f of 0, 1, 2, 3, 4. What's f of 0? For f of 0, plug in 0 for x. Plug in 0, 1, 2, 3, 4 into the probability function. F of 0, we have 4 choose 0, 1/3 to the power of 0, 2/3 to the power of 4. If we multiply out, that's 16 over 81. What's f of 1? F of 1, if I plug in 1 for x, we have 4 choose 1, 1/3 to the power of 1, 2/3 to the power of 3, if we multiply out, we have 32 over 81. What's f of 2? For f of 2, we plug in 2 for x. We get 4 choose 2. 1/3 to the power of 2. 2/3 to the power of 2. Together, that's 24 over 81. Next, what's f of 3? For f of 3, we plug in 3 for x. That's 4 choose 3. 1/3 to the power of 3. 2/3 to the power of 1. Together, that's 8 over 81. Next, f of 4. We plug in 4 for x. Plug in 4 for each x. We get 4 choose 4. 1/3 to the power of 4. 2/3 to the power of 0, which is 1 over 81. So we plug in 0, 1, 2, 3, 4 into the probability function. Next, we try to find the expected value. Since x is a binomial distribution, we know that it's a discrete random variable. So expected value for discrete random variable is the sum of all x in the support. X times f of x. The sum of all x in the support. X times f of x. So we have 0, 1, 2, 3, 4 in the support. So we have 0 times f of 0 plus 1 times f of 1 plus 2 times f of 2, 3 times f of 3 plus 4 times f of 4. Then plug in 0 times f of 0. F of 0 is 16 over 81. 1 times f of 1. F of 1 is 32 over 82. 32 over 81. 2 times f of 2. That's 2 times 24 over 81. 3 times f of 3. That's 3 times 8 over 81. Plus 4 times f of 4, which is 4 times 1 over 81. Then multiply and add them up. We have 81 on the denominator. On the numerator, we have 32 plus 48. That's 80. 80 plus 24. That's 104. 104 plus 1. That's 104 plus 4. That's 108. Okay, 108 over 81. If I divide top and bottom by 27, I get 4 over 3. That's the expected value of x. Next example, let x be the random variable with x has continuous uniform distribution from 2 to 10. Find the expected value of x. First step, let's find the PDF, the probability density function of x first. Since x has continuous uniform distribution, the PDF is f of x equal to 1 over beta minus alpha if x is between alpha and beta, and 0 otherwise. Here we know that alpha is 2, beta is 10. Alpha is 2, beta is 10. 10 minus 2 is 8, so we get 1 over 8. If s is between alpha and beta, alpha is 2, beta is 10. So s is between 2 and 10. That's the PDF, the probability density function of x. Next, let's find support of x. Since x has continuous uniform distribution, support of x is the closed interval from alpha to beta. Closed interval from alpha to beta. Here alpha is 2, beta is 10. So support of x is the closed interval from 2 to 10. Then since x is a continuous random variable, the expected value of x is the integral from negative infinity to infinity, x times f of x dx. Since x is a continuous random variable, then support of x is from 2 to 10. Support of x is from 2 to 10. So technical from 2 to 10. X times f of x. when x is between 2 and 10, when x is between 2 and 10, f of x is 1 over a. So you get x times 1 over a dx. Then take the antiderivative. Antiderivative of x is x squared over 2 times 1 over a. Evaluate from 2 to 10. That can be rewritten as 1 over 16 times x squared, evaluate from 2 to 10. If I plug in 10, 10 squared is 100. If I plug in 2, 2 squared is 4. 100 minus 4 is 96. 96 divided by 16 is 6. So expected value of x is 6. Next, let me introduce mathematical expectation of a function of a random variable. Mathematical expectation of a function of a random variable. First of all, let me show you a theorem. Let x be a random variable. With probability function or probability density function, f of x let g from real number to real number. Let g be a function from real number to real number. Then expected value of g of x is the sum of all x in the support. The sum of all x in the support. G of x, this is capital X, this is lowercase x. G of x times f of x. If x is discrete, if x is a discrete random variable, if x is discrete, and the expectation of g of x, this is capital X, is the integral from negative infinity to infinity. G of x times f of x, this is lowercase x, this is capital X. Integral from negative infinity to infinity, g of x times f of x dx. If s is a continuous random variable, if s is a continuous random variable, the actual proof of this theorem is very hard. The general proof of this theorem is very hard. Here, I will skip the proof. Memorize the theorem. Next, let's look at an example. Let the probability function of a random variable x be f of x, where f of x is 0.1 if s is negative 4, 0.2 if s is 1, 0.3 if s is 2, 0.4 if s is 5, 0 otherwise. Find the expected value of s squared, expected value of s cubed, expected value of 2s plus 1, and expected value of 5. First of all, let's find the support of x first. Here, support of x is negative 4, 1, 2, and 5. Support of x here is the set of all possible values of x. S could be negative 4, s could be 1, s could be 2, s could be 5. Negative 4, 1, 2, 5. That's support of x. Then let's try to find expected value of s squared. Since x is a discrete random variable, for expected value of s squared, we take the sum of all x in the support. S squared times f of x. take the function inside the parentheses times f of x. For expected value of a function of x, take the function in the parentheses times f of x. Then support of x is from negative 4, 1, 2, and 5. So when s is negative 4, we have negative 4 squared times f of negative 4. When s is 1, we have 1 squared times f of 1. When s is 2, we have 2 squared times f of 2. When s is 5, we have 5 squared times f of 5. Then plug in. Negative 4 squared is 16. F of negative 4, when s is negative 4, f of s is 0.1. So f of negative 4 is 0.1. Next, 1 squared is 1 times f of 1 times f of 1. When s is 1, f of s is 0.2. Plus 2 squared times f of 2. 2 squared is 4. F of 2. When s is 2, f of s is 0.3. So f of 2 is 0.3. Plus 5 squared times f of 5. 5 squared is 25. F of 5. When s is 5, f of s is 0.4. Then multiply out. That's 1.6 plus 0.2 plus 1.2 plus 10.0. Then adding up, that's 3.0. 3.0 plus 10.0 is 13. So expected value of s squared is 13. Next, let's compute expected value of s cubed. Expected value of s cubed. Since x is a discrete random variable, we take the sum of all x in the support. Then take the function in the parentheses. Take the function in the parentheses s cubed times f of x. Take the function in the parentheses times f of x. Here, support of x. Support of x is the set of negative 4, 1, 2, and 5. When s is negative 4, we have negative 4 cubed times f of 4. When s is 1, we have 1 cubed times f of 1. When s is 2, we have 2 cubed times f of 2. When s is 5, we have 5 cubed times f of 5. Then calculate. Negative 4 cubed is negative 64. F of negative 4. F of negative 4 is 0.1. 1 cubed is 1. F of 1 is 0.2. 2 cubed is a. F of 2 is 0.3. Here 1 cubed is 1. 5 cubed is 125. F of 5 is 0.4. Negative 64 times 0.1 is negative 6.4. 1 times 0.2 is 0.2, 0.2. 0.8 times 0.3 is 2.4. 125 times 4 is 50.0. Then adding up. Negative 6.4 plus 2.4 is negative 4. Negative 4 plus 50 is 46. 46 plus 0.2 is 46.2. That's the expected value of s cubed. That's the expected value of s cubed. Next, find the expected value of 2s plus 1. Next, Find the expected value of 2x plus 1. Expected value of 2x plus 1. Since x is a discrete random variable, we take the sum of all x in the support. Take the function in the parentheses. This is capital X, but when we plug in, we use lowercase x. 2x plus 1. Here we use lowercase x. In the parentheses here, this is capital X. When we plug in here, we use lowercase x. 2x plus 1 times f of x. They are both lowercase x. Take the function in the parentheses, multiply by f of x. Then, for all x in the support, x is -4, 1, 2, and 5. If I plug in -4, I have 2 times -4 plus 1 times f of -4. If I plug in 1, I have 2 times 1 plus 1 times f of 1. If s is 2, I have 2 times 2 plus 1 times f of 2. If s is 5, I have 2 times 5 plus 1 times f of 5. Then calculate this. 2 times -4 is -8. -8 plus 1 is -7 times f of -4. f of -4 is 0.1. 2 times 2. 2 times 1 is 2. Plus 1 is 3. Times f of 1. f of 1 is 0.2. 2 times 2 is 4. 4 plus 1 is 5. 5 times f of 2. f of 2 is 0.3. Plus 2 times 5 is 10. 10 plus 1 is 10. 10 plus 1 is 11. 11 times f of 5. f of 5 is 0.4. Then multiply. -7 times 0.1 is -0.7. 3 times 0.2 is -0.6. 4 times 0.3 is 1.5. 11 times 0.4 is 4.4. Then adding up. 0.6 plus 4.4 is 5. -0.7 plus 1.5 is 0.8. 5 plus 0.8 is 5.8. That's the expected value of 2s plus 1. That's the expected value of 2s plus 1. Next, find the expected value of number 5. Find the expected value of number 5. That's the sum of all x in the support. Since x is discrete random variable, that's the sum of all x in the support. Take the function in the parentheses. 5 times f of x. Then for all x in the support, we have -4, 1, 2, and 5. When s is -4, number 5 stays the same. Times f of -4. When s is number 1, number 5 here stays the same. Times f of 1. When s is 2, number 5 stays the same. We get 5 times f of 2. When s is 5, number 5 stays the same. We get 5 times f of 5. Then calculate each of them. f of -0.4 is 0.1. f of number 1 is 0.2. f of 0.2 is 0.3. 5 times f of 5. f of 5 is 0.4. And then multiply adding up. 5 times 0.1 is 0.5. 5 times 0.2 is 1.0. 5 times 0.3 is 1.5. 5 times 0.4 is 2.0. Then adding up. 0.5 plus 1.5 is 2. 1 plus 2 is 3. 2 plus 3 is 5. So expected value of number 5 is number 5. Expected value of number 5 is number 5. Next example. Let the probability density function of a random variable x be f of x, where f of x is 4x cubed if s is between 0 and 1, and 0 otherwise. Find the expected value of s plus 1, expected value of s squared, expected value of square root of x, and expected value of 2. First step, let's find the support of x first. support of x here is the interval from 0 to 1. For support of x, always use closed interval from 0 to 1. That's support of x. So always find support of x first. When we try to find expected values, always find support of x first. Then, based on the support, find each of the expected value. First one, expected value of x plus 1. This is capital X. Now, since this x is a continuous random variable, for the expected value, we use integral from net infinity to infinity. Then use the function in the parentheses. When we use the function in the parentheses, we write lowercase x plus 1 times f of x dx. So when we put the function here, write lowercase x. For expected value, this x must be capital X. And when we plug in, write lowercase x plus 1. And then support of x is from 0 to 1. Support of x is from 0 to 1. So take integral from 0 to 1. S plus 1 times f of x. Here, when s is between 0 and 1, f of x is 4s cubed. Then distribute 4s cubed. We get 4x to the power 4 plus 4s cubed dx. Then take antiderivative. Take antiderivative. We have 4x to the power 5 over 5 plus x to the power 4. Evaluate from 0 to 1. If I plug in 1, I get 4 over 5 plus 4. If I plug in 0, I get 0. So the final answer is 24 over 5. The final answer is 24 over 5. That's the expected value of x plus 1. That's the expected value of x plus 1. Next, let's compute expected value of x squared. This is capital X. Since x is a continuous random variable, take integral from net infinity to infinity. Put a function in the front. Put a function in the front here. Put a function inside the integral. When I plug in the function, I write lowercase x squared times f of x dx. And support of x is from 0 to 1. Support of x is the interval from 0 to 1. So take integral from 0 to 1. S squared times f of x. F of x, where s is between 0 and 1, f of x is 4s cubed. 4s cubed dx. Then if we simplify, I multiply s squared and s cubed. I have integral from 0 to 1, 4x to the power 5 dx. Then take an antiderivative. That's 4x to the power of 6 over 6. Evaluate from 0 to 1. If I plug in 1, I get 4 over 6. If I plug in 0, I get 0. So the final answer is 2 over 3. That's the expected value of x squared. That's the expected value of x squared. Next, let's try to find expected value of square root of x. Expected value of square root of x. Since x is a continuous random variable, we take integral from net infinity to infinity. Then use the function in the parentheses, square root of x. When we plug in the function in the parentheses, use lowercase x times f of x dx. Since support of x is from 0 to 1, we take integral from 0 to 1. Square root of x times f of x. Here f of x is 4s cubed. When s is between 0 and 1, f of x is 4s cubed dx. Then simplify. Square root of x, this is x raised to a half. When I multiply, I add the powers. Half plus 1/3 is 7 over 2. Half plus 3 is 7 over 2. So I have integral from 0 to 1. 4 times x raised to 7 over 3. 7 over 2 dx. Then take antiderivative. We have 4 times x to the power of 9 over 2 over 9 over 2. Evaluate from 0 to 1. Let me simplify this expression first. We'll have something divided by a fraction. We can multiply this by the reciprocal of the fraction. So this can be rewritten as 4 times 2 over 9. Some expression divided by a fraction is the same as taking expression times its reciprocal on the bottom, times x raised to 9 over 2. Evaluate from 0 to 1. If I plug in 0, I get 0. If I plug in 1, I get 4 times 2 over 9 times 1. 1 raised to any power is 1. So the final answer is 8 over 9. So the expected value of square root of x is 8 over 9. Expected value of square root of x is 8 over 9. Next, let's find expected value of 2. Expected value of 2. Since x is a continuous random variable, take integral from negative infinity to infinity, and then take the function in the parentheses multiplied by f of x. Take 2 times f of x dx. And then we know that support of x is from 0 to 1. So take integral from 0 to 1. 2 times f of x. When s is between 0 and 1, f of x is 4x cubed. When s is between 0 and 1, f of x is 4x cubed. Then simplify. We get integral from 0 to 1, ax cubed dx. Then take antiderivative. Take antiderivative, we get as to the power 4 over 4. Evaluate from 0 to 1. If I plug in 0, I get 0. If I plug in 1, I get a over 4, which is 2. So the expected value of 2, expected value of 2 is 2. Expected value of 2 is 2. Next example, the x being a random variable with x has an exponential distribution with theta equal to a half. Find the expected value of 2s plus 1, expected value of s squared, and the expected value of number 6. Here, x has exponential distribution with theta equal to a half. Let's first of all find a PDF. Find the probability density function of x first. The formula for PDF is 1 over theta e raised to negative x over theta if s is greater or equal to 0 and 0 otherwise. That's the PDF for exponential distribution. That's the PDF for exponential distribution. And here we know that theta is half. So we plug in half for each theta. Plug in half for each theta. 1 over half is 2. If I plug in half here, 1 over half is 2. So 1 over theta becomes 2. Negative x over theta. Theta is half. Negative x over half means negative x times 2, which is negative 2x. So we have e raised to negative 2x. That's a PDF. This is a probability density function of x. Next, find support of x. Since x has an exponential distribution, support of x is always an interval from 0 to infinity. Since x has exponential distribution, support of x is always from 0 to infinity. Interval from 0 to infinity, including 0. Now, let's find the expected value here. First one, expected value of 2s plus 1. Here, since s is a continuous random variable, we take integral. Take integral from negative infinity to infinity, and use the function in the parentheses, multiplied by the PDF. When we plug in the function in the parentheses, use lowercase x. Here, this x is capital letter. When we plug in, use lowercase x. 2s plus 1 times f of x dx. And we know that support of x is from 0 to infinity. So take integral from 0 to infinity. 2s plus 1 times f of x. When s is from 0 to infinity, f of x is 2 times e raised to negative 2x. So times 2 raised to negative 2x dx. Then this integral can be rewritten as integral from 0 to infinity. If I distribute 2, I have 4x plus 2 times e raised to negative 2x dx. For this integral here, I can use integration by parts. The u equal to 4s plus 2. dv equal to e raised to negative 2x dx. Take derivative for u. Du is 4 dx. Take antiderivative for v. We have negative 1 over 2 e raised to negative 2x. Then use the formula. U times v is negative 1 over 2 times 4s plus 2 raised to times e raised to negative 2x. U times v minus integral of v times u, v times du. So negative half times 4 is negative 2 e raised to negative 2x dx. And the limit here stays the same, from 0 to infinity, from 0 to infinity. If I distribute negative half here, I get negative 2x minus 1 e raised to negative 2x. Evaluate from 0 to infinity. If I take antiderivative here, I have negative double negative is positive 2 times negative 1 over 2 times e raised to negative 2x. Evaluate from 0 to infinity. And here 2 times negative half is negative 1. I can combine these two terms together. They have the same limit. I can combine them together. Consider there's a negative 1 here. Negative 1, if I combine line term, negative 1 plus negative 1 is negative 2 here. I get negative 2x minus 2 times e raised to negative 2x. Evaluate from 0 to infinity. If I plug in infinity, I get infinity here, negative infinity, e raised to negative infinity is 0. We got infinity times 0. If I plug in infinity, I got infinity times 0. So we must take a limit here. So let's take a limit here. I take limit as t approaches to infinity. If I plug in t, I get negative 2t minus 2 e raised to negative 2t. I take limit as t approaches to infinity. Then plug in t for each x. I get negative 2t minus 2 times e raised to negative 2t. Then this function can be rewritten as negative 2t minus 2 over e raised to positive 2t. If I bring e to the bottom, I make exponent positive. Now if I plug in infinity, on the numerator, I get negative infinity. On the bottom, I get infinity. It's in the form of infinity or infinity. We can use L'Hopital's rule here. If we use L'Hopital's rule here, on the numerator, I get negative 2. On the denominator, I get 2 times e to the power of 2t. If I plug in infinity one more time, e to the power of infinity is infinity. 2 times infinity is infinity. Negative 2 over infinity is 0. Negative 2 over infinity is 0. So if I plug in infinity, I get 0. Since the limit is 0. That means if I plug in infinity, I get 0. If I plug in infinity, I get 0. What if I plug in 0? If I plug in 0, what do we get? Negative 2 times 0 is 0. 0 minus 2 is negative 2. If I plug in 0 here, e raised to power 0 is 1. So we get 0 minus negative 2, which is positive 2. So the expected value of 2s plus 1 is positive 2. Expected value of 2s plus 1 is positive 2. Next, let's compute expected value of s squared. Next, let's compute expected value of s squared. Since x is a continuous non-variable, we take integral. Take integral from negative infinity to infinity. Use the function in the parentheses, s squared times f of x dx. And we know that support of x is from 0 to infinity. Support of x is from 0 to infinity. So we take the integral from 0 to infinity. S squared times f of x. When s is from 0 to infinity, f of x is 2 times e raised to negative 2x. F of x is 2 times e raised to negative 2x dx. this function can be rewritten as integral from 0 to infinity 2x squared e raised to negative 2x dx. Here we need to use integration by parts. Let u be 2x squared, dv be e raised to negative 2x dx. Then take derivative for u, we get 4x dx. Take antiderivative for dv, I get negative 1 over 2 e raised to negative 2x. Then use the formula u times v. U times v, that's negative x squared times e raised to negative 2x minus v times du, integral of v times du. V times du, negative half times 4 is negative 2. Times e raised to negative 2x dx. And the limit is from 0 to infinity. Limit is from 0 to infinity. Then here I can pull out negative sign. If I pull out negative sign, I get positive integral from 0 to infinity 2x e to the power of negative 2x dx. And for this part, we need to do integration by part one more time. For this part, do integration by part one more time. Here, let u be 2x, dv be e raised to negative 2x dx. Take integration by part one more time. Du is 2 dx. V is negative 1 over 2 e raised to negative 2x. Then use the formula for this for the second part. U times v. 2 times negative half is negative 1. I get negative x e raised to negative 2x. U times v minus integral of v times du. Negative 1 over 2 times positive 2 is negative 1. E raised to negative 2x dx. And the limit is from 0 to infinity. Limit is from 0 to infinity. And don't forget the first term. First term is negative x squared e raised to negative 2x from 0 to infinity. Then I can pull out negative sign here. Take antiderivative. If I pull out negative sign, it becomes positive. If I pull out negative sign, it becomes positive. E raised to negative 2x. If I take antiderivative, that's negative 1 over 2 e raised to negative 2x. Evaluate from 0 to infinity. Now, they all have the same limits here. I can combine like terms. If I combine like terms, I get negative x squared minus x plus half minus half. Times e raised to negative 2x. Evaluate from 0 to infinity. If I plug infinity, I get negative infinity. If I plug infinity, I get negative infinity here. If I plug infinity, e raised to negative infinity is 0. I get infinity times 0. Again, need to use L'Hopital's rule. This is indeterminate form. Need to use L'Hopital's rule. So let me write it as a limit first. Limit as t approaches to infinity. If I plug in t for x, I have negative t squared minus t minus half times e raised to negative 2t. So plug in t for each x, then take limit as t approaches to infinity. First of all, this function can be rewritten as limit as t approaches to infinity, negative t squared minus t minus half over e raised to negative 2t over e raised to positive 2t. If I bring e to the bottom, I make exponent positive. Then if I plug infinity, I get infinity over infinity. Here we can apply L'Hopital's rule. I can apply L'Hopital's rule. If I apply L'Hopital's rule here, take derivative from the numerator, I get negative 2t minus 1. On the bottom, I get 2 times e raised to power of 2t. If I plug infinity, it's still infinity over infinity. If I plug infinity, it's still infinity over infinity. So use L'Hopital's rule one more time. If I use L'Hopital's rule one more time, the numerator is negative 2. Denominator is 4 times e to the power of 2t. If I plug infinity here, e raised to infinity is infinity. So negative 2 over infinity is 0. So we get 0. This limit is 0. That means if I plug in infinity for each x, I get 0. If I plug in 0 for x, I get negative half. E to the power of 0 is 1. Together is positive half. So its better value of s squared, its better value of s squared is half. Its better value of s squared is half. Next, find its better value of 6. Its better value of 6. Since x is a continuous non-variable, take integral from negative infinity to infinity. Use number 6, use the function in the parentheses times f of x dx. And here, since support of x is from 0 to infinity, support of s is from 0 to infinity. So take integral from 0 to infinity. 6 times f of x. F of x, if s is greater than 0, f of x is 2 times e raised to negative 2x. dx. 6 times 2 is 12. So I got 12. Integral from 0 to infinity, e raised to negative 2x dx. If I take antiderivative, I have 12 times negative 1 over 2, e raised to negative 2x. Evaluate from 0 to infinity. Here, 12 times negative half is negative 6, e raised to negative 2x. From 0 to infinity. If I plug in infinity, e raised to negative infinity is 0. If I plug in 0, e to the power of 0 is 1. So I get 0 minus negative 6, which is positive 6. So that means its better value of 6 is 6. Its better value of 6 is number 6 itself. Next example, when two dice are rolled, let the random variable x represent the difference of the two dice. Find the expected value of 3x, expected value of x squared, and expected value of number 4. First of all, let's find the probability function for x first. So when two dice are rolled, let's draw the sample space first. When two dice are rolled, we make it 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. Here, X represents the difference of the two dice. Difference between 1 and 1 is 0. Difference between 1 and 2 is 1. Difference between 1 and 3 is 2. 3, 4, and 5. Difference between 2 and 1 is 1. Difference between 2 and 2 is 0. Distance between 2 and 3, difference between 2 and 3 is 1. Difference between 2 and 4 is 2. 3 and 4. Difference between 3 and 1 is 2. Difference between 3 and 2 is 1. Difference between 3 and 3 is 0. Difference between 3 and 4 is 1. Difference between 3 and 5 is 2. Difference between 3 and 6 is 3. Difference between 4 and 1 is 3. 2, 1, 0, 1, 2. Difference between 5 and 1 is 4. Difference between 5 and 2 is 3. Difference between 5 and 3 is 2. 1, 0, 1. Difference between 6 and 1 is 5. Difference between 6 and 2 is 4. Difference between 6 and 3 is 3. 2, 1, 0. Next, let's find support of X. Support is the set of all possible X value. The set of all possible X value. Support of X is a set of all possible values that S could be. Here S could be 0, 1, 2, 3, 4, 5. S could be 0, 1, 2, 3, 4, 5. That's support of X. Then we find probability for each value here, for each value in the support. Then we find a probability for each value in the support. What's f of 0? F of 0 is probability that S equal to 0. F of 0 is a probability that S equal to 0. Here S equal to 0, 0 occurs 1, 2, 3, 4, 5, 6. 0 occurs 6 times out of a total of 36 outcomes. So that's 6 over 36. What's f of 1? F of 1 is probability that S equal to 1. Number 1 occurs how many times? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. S equal to 1 occurs 10 times. So the probability is 10 over 36. Number of available outcome over number of all possible outcome. 10 over 36. What's f of 2? F of 2 is probability that S equal to 2. F of 2 is probability that S equal to 2. Number 2 occurs how many times? 1, 2, 3, 4, 5, 6, 7, 8. Number 2 occurs 8 times. So f of 2 is 8 over 36. What's f of 3? F of 3 is probability that S equal to 3. Number 3 occurs how many times? 1, 2, 3, 4, 5, 6. 3 occurs 6 times. So f of 3 is 6 over 36. What's f of 4? F of 4 is probability that S equal to 4. Number 4 occur 1, 2, 3, 4 occur 4 times, which is 4 over 36. F of 5. Number 4 occurs twice. 1, 2. That's 2 over 36. So find probability for each X. Find probability for each value in the support. Then we can compute the expected value. Expected value of 3x. Here, since x is a discrete random variable, we find a sum for all x in the support. Find the sum for all x in the support. Then take 3x. This is lowercase x. This is capital X. This is lowercase x. Take the function in the parentheses, 3x times f of x. Here, the support is the value from 0 to 5, integers from 0 to 5. So I have 3 times 0 times f of 0 plus 3 times 1 times f of 1 plus 3 times 2 times f of 2 plus 3 times 3 times f of 3 plus 3 times 4 times f of 4 plus 3 times 5 times f of 5. Then plug in the values. 3 times 0 is 0. F of 0 is 6 over 36. 3 times 1 is 3 times f of 1. F of 1 is 10 over 36. Three times 2 is 6 times f of 2. F of 2 is 8 over 36. Three times 3 is 9. 9 times f of 3. F of 3 is 6 over 36. Three times 4 is 12. 12 times f of 4. F of 4 is 4 over 36. Three times 5 is 15 times f of 5. F of 5 is 2 over 36. Then multiply. We have 30 over 36 plus 48 over 36 plus 54 over 36 plus 48 over 36 plus 30 over 36 all over 36. Together is 210 over 36. Adding up, we get 210. 210 over 36. Then we can divide top and bottom by 6. We get 35 over 6. That's the expected value of 3x. Next, we try to find the expected value of x squared. For expected value of x squared, since x is a discrete random variable, we take the sum for all x in the support. Then take x squared times f of x. Always take the function in the parentheses times f of x. Here the function in the parentheses is x squared, so we put x squared times f of x. Always put lowercase x squared here. This is capital X. This is capital X in the parentheses. This is lowercase x. Then here, support of x is numbers from 0, integers from 0 to 5. So we have, if I plug in, I have 0 squared times f of 0 plus 1 squared times f of 1 plus 2 squared times f of 2 plus 3 squared times f of 3 plus 4 squared times f of 4 plus 5 squared times f of 5. Then multiply. 0 squared is 0. F of 0 is 6 over 36. 1 squared is 1. F of 1 is 10 over 36. 2 squared is 4. F of 2 is 8 over 36. 3 squared is 9. F of 3 is 6 over 36. 4 squared is 16. F of 4 is 4 over 36. 5 squared is 25. F of 5 is 2 over 36. Then multiply. In the numerator, 1 times 10 is 10. 4 times 8 is 32. 9 times 6 is 54. 16 times 4 is 64. 25 times 2 is 50. over 36. Then adding up, I get 210 over 36. If I simplify, I can divide top and bottom by 6, which is 35 over 6. That's expected value of s squared, which is 35 over 6. Next, we try to find expected value of number 4. For expected value of number 4, since x is a discrete random variable, we take the sum for all x in the support. Then take the function in the parentheses times f of x. Here, since support of x is integers from 0 to 5, so we have 4 times f of 0 plus 4 times f of 1 plus 4 times f of 2 plus 4 times f of 3 plus 4 times f of 4 plus 4 times f of 5. F of 0 is 6 over 36. F of 1 is 10 over 36. F of 2 is 8 over 36. F of 3 is 6 over 36. F of 4 is 4 over 36. F of 5 is 2 over 36. Then let's multiply. On the numerator, 4 times 6 is 36, it's 24. 4 times 10 is 40. 4 times 8 is 32. 4 times 6 is 24. 4 times 4 is 16. 4 times 2 is 8. If we add them up, here we get 144 over 36. 144 over 36 is 4. So expected value of 4 is number 4 itself. Expected value of number 4 is number 4 itself. Next, let me introduce a theorem. Let x be a random variable with probability function or probability density function f of x. Then we have two statements. Expected value of any constant c equal to c, where c is a constant. Also, expected value of a0 plus a1x plus a2x squared plus ansn equal to a0 plus a1 times expected value of x plus a2 times expected value of s squared plus an times expected value of s to the power of n. Let's prove it. Let's prove the first one first. Let's consider two cases. X is a random variable. It could be either discrete or continuous. Let's prove this in two cases. Case 1. S is a discrete random variable. If S is a discrete random variable, expected value of X, expected value of C is the sum of all X in the support. The sum of all X in the support. C times f of X. Take the number in the parentheses. C times f of x. Then here, since c is a constant, I can pull it outside the summation. Since c is a constant, I can pull it outside the summation. It's c times the sum of all x in the support times f of x. Since f of x is a probability function, the sum of all probability is 1. The sum of all probability is 1. So here c times 1 equal to c. The sum of all probability is 1, and c times 1 is c. So that proves that expected value of c equal to c if s is a discrete random variable. Now case 2, let's consider x is a continuous random variable. Case 2, let's consider x is a continuous random variable. Then expected value of c is the integral from negative infinity to infinity. Take c times the probability density function of x. Take c times f of x dx. And then for integrals, we can always pull out constant. Since c is a constant, I can pull out c. If I pull out c, I get c times negative infinity, integral from negative infinity to infinity, f of x dx. And we know that since f of x is a CDF, since f of x is a PDF, since f of x is a PDF, the total area under the curve must be 1. The total area under the curve must be 1. So the integral from negative infinity to infinity f of x dx must be 1. And we know that c times 1 is c. That proves that expected value of c equal to c if s is a continuous random variable. So let's complete the proof for the first statement. For the second statement, we also prove it in 2 ways. We also prove it in 2 cases. For the second statement, we also prove it in 2 cases. Case 1. X is a discrete random variable. So expected value of a0 plus a1 x plus a2 s squared plus an sn. It can be noted as the sum of all x in the support. The sum of all x in the support. Take the function in the parentheses. Times f of x. Here use lowercase x. Take the function in the parentheses times f of x. Then I can distribute f of x into the parentheses. If I distribute f of x, I get a0 f of x plus a1x f of x plus a2x a2s squared f of x plus the last one an sn an s to the power n f of times f of x. Then I can split the summation. But as the sum of all x a0 f of x. Here I don't write this. It should be x belong to support of x. I didn't run a full name here. It should be x belong to support of x. The sum of all x a1 x f of x. I can split the summation plus the sum of all x a2 x squared f of x plus the sum of all x an Sn f of x. Here the base here should be x belong to support of x. Everyone here should be x belong to support of x. Then here we consider a0, a1, a2, an, they are constants, so polar constant. I get a0 times the sum of all x f of x plus a1 times the sum of all x times f of x plus a2 times the sum of all x squared times f of x plus an times the sum of all x to the power n times f of x. Then we know that since f of x is a probability function, the sum of all probability must be 1. Since f of x is a probability function, the sum of all probability must be 1. So here a0 times 1 must be a0. Here a1 stays the same. The sum of all x times f of x, that's the expected value of x. The sum of all x times f of x, that's the expected value of s. Next, plus a2 times the sum of all x squared times f of x, that's the expected value of s squared. This is capital X. The sum of all x squared times f of x, that's expected value of s squared. Plus the last one, an stays the same. The sum of all x to the power n times f of x, that's expected value of x to the power of n. So if s is discrete random variable, we prove that expected value of a0 plus a1x plus a2 s squared plus an s to the power n equal to a0 plus a1 expected value times expected value of x plus a2 times expected value of s squared plus an times expected value of x to the power of n. That's the first part. That's the first case. S is a discrete random variable. Case 2, we must prove that when S is continuous random variable, this statement is also true. Case 2, X is a continuous random variable. If S is a continuous random variable, expected value of a0 plus a1 x plus a2 s squared plus an times s to the power of n, that can be written as integral from negative infinity to infinity. Take the function in the parentheses, multiply by f of x. If s is a continuous random variable, take integral from negative infinity to infinity. Then take a function in the parentheses, a0 plus a1x, use lowercase x, plus a2 s squared plus an xn times f of x dx. Then I can distribute f of x. If I distribute f of x, I have a0 times f of x plus a1x times f of x plus a2s squared times f of x plus ansn times f of x dx. Then I can separate the integral into n terms. I can separate this integral into n integrals. This integral can be rewritten as integral from negative infinity to infinity a0 f of x dx plus integral from negative infinity to infinity a1x times f of x dx plus integral from negative infinity to infinity a2 x squared times f of x dx plus plus integral from negative infinity to infinity ansn times f of x dx. Then on each integral, I can pull out a0, a1, a2, an. On each integral, pull out a0, a1, a2, an. If I pull out a0, I get integral from negative infinity to infinity f of x dx. If I pull out a1, I get a1 times integral from negative infinity to infinity x f of x dx. If I pull out a2, I get a2 times integral from negative infinity to infinity x squared f of x dx. In the last integral, I pull out an. I get an times integral from negative infinity to infinity x to the power n times f of x dx. Then, since f is a PDF, probability density function of x, the total area under the curve is 1. Since f is a PDF probability density function, the total area under the curve must be 1. So if I take integral from negative infinity to infinity, I must get 1. And here we know that a0 times 1 is a0. For the second integral from negative infinity to infinity x times f of x dx, that's the expected value of x. Next we get a2 times integral from negative infinity to infinity s squared times f of x dx. That's the expected value of s squared. Last one, we have an times integral from negative infinity to infinity s to the power n times f of x dx. That's the expected value of s to the power of n. So let's prove that this part shows that expected value of a0 plus a1x plus a2 s squared plus an sn equal to a0 plus a1 times expected value of x plus a2 times expected value of s squared plus an times expected value of s to the power of n, if s is a continuous non-variable. So let's complete the proof for the second statement. Next, let me show you a corollary based on the previous theorem. A corollary is a simple theorem. Let x be a random variable. Then, expected value of ax plus b equal to a times expected value of x plus b, where a and b are constants. According to the previous theorem, the second part says expected value of n-degree polynomial. For expected value of n-degree polynomial, I can separate the terms. Separate each terms, and then pull out the constant. Separate each terms, then pull out constant. In the first term, expected value of a0 is a0 itself. So for the other terms, I can pull out constant. This is true for any n-degree polynomial. And here, as plus b is a first-degree polynomial. So I can separate the terms. In the first term, pull out a. In the second term, expected value of b is b itself. So that's a simple corollary based on the previous theorem. Note: in general, expected value of x is called the first moment of x. Expected value of x squared is called the second moment of x. It's called the second moment of x. And expected value of x raised to power n is called the n moment of x. expected value of x is called the first moment of x. Expected value of x squared is called the second moment of x. Expected value of x raised to power n is called the n moment of x. Those are some terminologies. Keep it in mind. Next, let's do a simple example. Let x be a random variable. Whose first, second, and the third moment are 1, 4, and 6, respectively. Evaluate each of the following expressions. Part A. Expected value of 2 plus x plus x cubed. How to evaluate this? According to the previous theorem, this can be rewritten as 2 plus expected value of x plus expected value of x cubed. I can first of all separate the terms. Then plug in. We know that the first moment is 1, second moment is 4, third moment is 6. That means expected value of x is 1. Expected value of x squared is 4. Expected value of x cubed is 6. Number 2 stays the same. Expected value of x is 1. Expected value of x cubed is 6. That's the first moment, that's the third moment. Expected value of number 2 stays the same. So 2 plus 1 plus 6 is 9. Part B. What's the expected value of x cubed? Minus 2x squared minus 6. By the previous theorem, I'm allowed to separate the terms first. I get expected value of x cubed plus expected value of negative 2x squared plus expected value of negative 6. Then I can pull out constants. I get expected value of x cubed minus 2 power negative 2 minus 2 times expected value of x squared, and expected value of constant is the constant itself. Then expected value of x cubed is the third moment. The third moment is 6. Expected value of x squared is the second moment. Second moment is 4 minus 6. Then multiply, adding up. 6 and negative 6 can cancel. Negative 2 times 4 is negative 8. Next, let me introduce variance and standard deviation. Let x be a random variable. With expected value of x equal to mu. Then the variance of x is defined as variance of x equal to variance of x equal to expected value of x minus mu squared. That's how we define variance. And the standard deviation of x usually use sigma represent standard deviation. That's the Greek letter sigma. They're equal to square root of the variance. The standard deviation of x equal to the square root of the variance of x. Next, let me put all the definitions together. We know that expected value of x is mu equal to e of x. Sometimes it's also called a mean. Variance of x is the expected value of x minus mu squared, and the standard deviation of x is sigma equal to square root of variance of x. So keep this in mind. Based on this definition here, keep one relationship in mind. Sometimes sigma square equal to variance of x. Sometimes we write it this way: sigma square equal to variance of x. That's equivalent to this definition here. Sigma square equal to variance of x. This is equivalent to this. Next, let's look at an example here. We're rolling a die. Let the random variable x represent the outcome of the die. Find the variance and the standard deviation of x. First of all, let's recognize what kind of probability distribution x is. When we roll a die, the outcome could be 1, 2, 3, 4, 5, or 6. Every number has the same chance to come up. So this is discrete uniform distribution. So this x is a discrete uniform distribution. Over the set of numbers 1, 2, 3, 4, 5, 6. When we roll a die, there are 6 outcomes: 1, 2, 3, 4, 5, 6. And every number has the same chance to come up. This is uniform distribution. Then the formula for uniform distribution. The probability function for uniform distribution is 1 over n, where n is the size of this set. In the set there are 1, 2, 3, 4, 5, 6. There are 6 numbers. So the probability function f of x is 1 over 6. F of x is 1 over 6. If s is 1, 2, 3, 4, 5, 6. And the support of x is all x in the set here. 1, 2, 3, 4, 5, 6. The set of all parts of x value. X represents the outcome of the die. So x could be 1, 2, 3, 4, 5, or 6. That's the setup. Next, let's try to find the variance and standard deviation. Next, we try to find the variance and the standard deviation. Variance is expected value of x minus mu squared. We need to find mu first. Mu is expected value of x. Mu is expected value of x. So let's find mu first. Mu is expected value of x. Since x is a discrete random variable, we take the sum for all x in the support. Take the sum for all x in the support. It's x. Then we use x times f of x. For all x in the support, we have x equal to 1, 2, 3, 4, 5, or 6. So we have 1 times f of 1, 2 times f of 2. Let me put it here. 1 times f of 1, 2 times f of 2, 3 times f of 3, 4 times f of 4, 5 times f of 5, and 6 times f of 6. Then we know that f of 1, when s is 1, f of s is 1 over 6. F of 1 is 1 over 6. F of 2, when s is 2, f of s is also 1 over 6. For f of 3, if s is 3, f of s is also 1 over 6. 4 times 1 over 6, 5 times 1 over 6, 6 times 1 over 6. Together is 21 over 6, which is 7 over 2. That's the expected value. That's mu. Next, we compute the variance. Next, we compute the variance of x. Variance of x is expected value of x minus mu square. Mu here is 7 over 2 square. Since x is a discrete random variable, we take the sum. Take the sum for all x in the support. Take the function in the parentheses times f of x. X minus 7 over 2 square times f of x. And here we know that support of x is numbers from 1 to 6, integers from 1 to 6. We have, if we plug in, we have 1 minus 7 over 2 square times f of 1. If I plug in 1, that's what I get. If I plug in 2, I get 2 minus 7 over 2 square times f of 2. If I plug in 3, I have 3 minus 7 over 2 square times f of 3, and so on. And the last one is 6 minus 7 over 2 square times f of 6. Then compute each of them. 1 minus 7 over 2 is negative 5 over 2. Negative 5 over 2, when I square, I got 25 over 4 times f of 1. F of 1 is 1 over 6. 2 minus 7 over 2 is negative 3 over 2. When I square, I got 9 over 4. F of 2 is 1 over 6. Next, 3 minus 7 over 2 is negative 1 over 2. When I square, I get 1 over 4. F of 3 is 1 over 6. Next, 4 minus 7 over 2 is half. Half square is 1 over 2. It's 1 over 4. F of 4 is 1 over 6. Next, when s is 5. 5 minus 7 over 2 is 3 over 2. 3 over 2 square is 9 over 2. 9 over 4. F of 4 is 1 over 6. In the last term, 6 minus 7 over 2 is 5 over 2. 5 over 2, when I square, I get 25 over 4 times f of 6. F of 6 is 1 over 6. Then when I multiply, the denominator is 24 everywhere. Denominator is 24 everywhere. In the numerator, I get 25 plus 9 plus 1 plus 1 plus 9 plus 25. Together, it's 10, 20, 20 plus 50 is 70. 70 over 24. I can divide top and the bottom by 2. I get 35 over 12. That's the variance of x. Next, for the standard deviation of x. For the standard deviation of x, take square root of the variance. Take square root of the variance. I get square root of 35 over 12. That's the standard deviation of x. Next, let me give you some rough idea about variance and standard deviation. Let x be a random variable. Defined in an experiment. Defined in an experiment. Then, every time when we do the experiment, every time when we do the experiment, we obtain a number, we obtain a real number, we obtain a real number from support of x. Every time when we do the experiment, we obtain a real number from support of x. If we repeat the experiment, a large amount of times, and record what we obtained. If we repeat the experiment a large amount of times and record what we obtained, then we'll have a sequence of numbers we have a sequence of real numbers. The expected value of x. The expected value of x E of x is very close to the average of all these numbers. The expected value E of x is very, very close to the average of these numbers. The variance or the standard deviation represents a dispersion or spread of these values, of these numbers, of this number obtained from the experiments. In general, the smaller variance or standard deviation the more data value are near the mean, the more numbers are near the mean. The more numbers obtained from the experiment, the more numbers are near the mean. Mean means expected value. And the larger variance or standard deviation the larger variance of standard deviation, the more data value are far away from the mean. The more numbers are far away from the mean. Those are some rough ideas about variance and standard deviation. Next, let's do some computation about variance and standard deviation. Look at this example here. Let the probability function of the random variable x be f of x, where f of x is 1 over 6 if s is 2, 1 over 3 if s is 4, 1 over 2 if s is 6, 0 otherwise. Find the variance and the standard deviation of x. First of all, let's try to find the variance. Variance of x is expected value of x minus mu squared. What's mu? Mu is the expected value of x. So we must find mu first. Before we find the variance, we must find mu first. Mu is the expected value of x. Mu is the expected value of x. In order to find expected value of x, we must know support of x first. Support of x is the set of all possible outcomes of x. Here s could be 2, 4, or 6. So support of x is the set of 2, 4, and 6. Since x is a discrete random variable, for expected value of x, we find a sum for all x in the support. Since x is a discrete random variable, we find a sum for all x in the support. X times f of x. And for all x in the support, we have 2, 4, and 6. For all x in the support, we have 2, 4, and 6. If we find a sum, we have 2 times f of 2 plus 4 times f of 4 plus 6 times f of 6. And then we know that f of 2, where s is 2, f of s is 1 over 6. So f of 2 is 1 over 6. 4 times f of 4, where s is 4, f of s is 1/3. So f of 4 is 1/3. Plus 6 times f of 6, where s is 6, f of s is a half. Multiply, adding up, we have 1/3 plus 4/3 plus 3. Put it as 3 over 1. Adding up, we get 14 over 3. That's the expected value of x. That's the expected value of x, which is mu. This is mu. Next, we can find the variance. Once we know the mu, we can find the variance. Variance of x is the expected value of x minus mu squared. And we know that here, mu is 14 over 3. Here, mu is 14 over 3. Since x is a discrete random variable, we take the sum for all x in the support. Then using the function in the parentheses times f of x. X minus 14 over 3 squared times f of x. This is lowercase x, this is capital X. Use the function in the parentheses times f of x, and then find the sum for all x in the support. Find the sum for all x in the support. For all x in the support, we have 2, 4, and 6. So if s is 2, we have 2 minus 14 over 3 squared times f of 2. If s is 4, we have 4 minus 14 over 3 squared times f of 4. If s is 6, we have 6 minus 14 over 3 squared times f of 6. Then here, two minus 14 over 3 is negative 8 over 3. Negative 8 over 3 is 64 over 9 times f of 2. F of 2 is 1 over 6. Plus 4 minus 14 over 3 is negative 2 over 3. Negative 2 over 3 squared is 4 over 9 times f of 4. F of 4 is 1 over 3. Plus 6 minus 14 over 3. That's 4 over 3. 4 over 3 squared is 16 over 9 times f of 6. F of 6 is 1 over 2. Multiply, adding up, we have 32 over 27 plus 4 over 27 plus 8 over 9. 8 over 9 can be noted as 24 over 27. Adding up, 24 plus 4 is 28. 28 plus 32 is 60. We get 60 over 27, which can be reduced as 20 over 9. That's the variance of x. Next, for the standard deviation of x, we take square root for the variance of x. For the standard deviation, take square root for variance of x. If I take square root for 20 over 9, I get 2 radical 5 over 3. That's the standard deviation of x. That's the standard deviation of x. Next example, let the probability density function of the random variable x be f of x, where f of s equal to 3s squared if s is between 0 and 1, and 0 otherwise. Find the variance and the standard deviation of x. So let's find the variance first. Variance of x is always the expected value of x minus mu squared. But here we don't know mu. So in order to find the variance, we must find mu first. Mu is the expected value of x. Let's find mu first. Mu is the expected value of x. In order to find expected value of x, we must find support of x first. In order to find expected value of x, we must find support of x first. What's support of x here? Here, support of x is the set of all possible value of x. Here x could be any number between 0 and 1. If support of x is an interval, we must write it as a closed interval. If support of x is an interval, we must write it as a closed interval. So it's a closed interval from 0 to 1. That's support of x. Since this x is a continuous random variable, we take integral from negative infinity to infinity. X times f of x dx. Since support of x is from 0 to 1, we take integral from 0 to 1, x times f of x. When s is between 0 and 1, f of x is 3x squared dx. Then simplify and take antiderivative. If I multiply x and 3x squared, I have 3x cubed dx. Take antiderivative, I get 3x to the power of 4 over 4. Evaluate from 0 to 1. If I plug in 1, I get 3 over 4. If I plug in 0, I get 0. So the answer is 3 over 4. This is the expected value of x, which is also the mu, Now next, we can find the variance. Once we know mu, we can find the variance. Variance of x. That's the expected value of s minus mu squared. And here we know that the mu is 3 over 4. So we have expected value of x minus 3 over 4 squared. Then since this x is a continuous random variable, we take integral from negative infinity to infinity. Take the function in the parentheses. X minus 3 over 4 squared times the PDF f of x dx. Take the function in the parentheses times the PDF f of x. This is capital X. This is lowercase x. Be very careful. This is capital X, and this is lowercase x. Since support of x is from 0 to 1, support of x is the interval from 0 to 1. So take integral here from 0 to 1. Take integral from 0 to 1. X minus 3 over 4 squared times f of x. When s is between 0 and 1, f of x is 3x squared. When s is between 0 and 1, f of x is 3x squared dx. Now solve this integral. Let's first of all expand the perfect square. If I expand the perfect square, I get s squared minus 3 over 2x plus 9 over 16 times 3x squared dx. Distribute 3x squared. We have 3x to the power 4 minus 9 over 2x cubed plus 27 over 16 x squared dx. Then take an antiderivative. We get 3x to the power of 5 over 5 minus 9 over 2 times x to the power 4 over 4 plus 27 over 16 times x cubed over 3. Evaluate from 0 to 1. If I plug in 1, I get 3 over 5. If I plug in 1 here, I get 9 over 8. If I plug in 1 here, I get 9 over 16. If I plug in 0, I get 0 everywhere. Then simplify this. The least common denominator is 80. I have 48 minus 90 plus 45. which is 3 over 80. That's the variance. Next, for the standard deviation. For the standard deviation, take square root for the variance. Standard deviation is the square root of the variance, which is square root of 3 over 80. Which I can write as radical 3 over 4 radical 5. That's the standard deviation. Here we can see that finding the variance is not easy. Sometimes there are a lot of work. Is there a simpler way? The answer is yes, there is a simpler way. Let me show you a theorem. Theorem. Let x be a random variable. Then the variance of x is the expected value of x squared minus the expected value of x squared. First square is inside the parentheses. Second square is completely outside the bracket. Be very, very careful. They are not the same. Now let's prove it. We know that variance of x, by its definition, is the expected value of x minus mu squared. If I expand the perfect square here, what do we get? I get expected value of x squared minus 2 mu x plus mu squared. That's what I get if I expand the perfect square. Next, this is a polynomial, so I can separate the expected value into 3 terms. This is a polynomial. I can separate the expected value into 3 terms. I can write it as expected value of x squared plus expected value of negative 2 mu x plus expected value of mu squared. Expected value of x squared, I leave it the same. I don't want to simplify it, leave it the same. For the second term here, 2 mu is a constant, I can pull out constant. 2 mu is a constant, I can pull it outside. If I pull out negative 2 mu, I have e of x. I have the expected value of x. Plus the last term. Last term, expected value of mu squared. Mu is a constant, so mu squared is also constant. Expected value of a constant is the constant itself. Expected value of a constant is the constant itself. Then we know that mu, what's mu? Mu is e of x. Mu is the expected value of x. Plug in. I have expected value of x squared minus 2 times expected value of x times expected value of x plus expected value of x squared. And then I have e of x squared, expected value of x squared minus twice expected value of x squared. Expected value of x times itself is expected value of x squared plus expected value of x squared. If I combine like term here, they are like terms. If I combine like term here, I get expected value of x squared minus expected value of x squared. Let's complete the proof. Variance of x equal to expected value of x squared minus expected value of x squared. First square is inside the parentheses. Second square is outside the bracket. Be very, very careful. They are not the same thing. Now, let's use this new formula. Redo example 2 and example 3. Let's use this new formula. Redo example 2 and example 3. If I redo example 2, what do we have? We need to compute e of x squared and e of x. In example 2, we already compute expected value of x. We already know e of x, which is 14 over 3. We already know that e of x is 14 over 3. Next, we need to compute e of s squared. Next, in order to use the new formula, we must compute e of s squared. How do we compute e of s squared? In example 2, this x is a discrete random variable. So take the sum for all x in the support. Take the sum for all x in the support. Then take s squared times f of x. Take s squared times f of x. In example 2, the support contains only 3 numbers, 2, 4, and 6. So we plug in, we have 2 squared times f of 2 plus 4 squared times f of 4 plus 6 squared times f of 6. We know that 2 squared is 4. f of 2 is 1 over 6 plus 4 squared is 16 times f of 4. f of 4 here is 1/3. f of 4 is 1/3 plus 6 squared. 6 squared is 36 times f of 6. f of 6 is 1 over 2. f of 6 is 1 over 2. So together we have 2 over 3 plus 16 over 3 plus 18. 2 over 3 plus 16 over 3. That's 18 over 3. 18 over 3 is 6. 6 plus 18 is 24. That's e of s squared. Next, use the new formula. Variance of x is e of s squared minus e of x squared. Plug in. E of s squared is 24. E of x is 14 over 3 squared. Then square e of x, which is 24 minus 196 over 9. 24 times 9 is 216 minus 196 over 9, which is 20 over 9. So the variance is the same as what we get in part 2. The variance is exactly the same as we have here in part 2. But here, using this technique, using the old formula is much longer. Using the new formula, the computation is much shorter. If you use the new formula, the computation is much shorter. We get the same variance. And then for the standard deviation, take square root, that's easy. For the standard deviation, take square root, that's easy. The hard part is find the variance. Next, let's redo number 3, find the variance. Let's redo number 3, finding the variance using the new formula. Let's redo example 3. Find the variance using the new formula. So to find the variance using the new formula, we must know e of x and e of s squared. We must know the expected value of x and expected value of s squared. Number 3 here, we know that expected value of x is 3 over 4. We know e of x already. From number 3 here, we know that expected value of x is 3 over 4. We know that already. So expected value of x is 3 over 4. And we know that already. Next, we try to compute expected value of x squared. In order to use a new formula, we must compute expected value of x squared. Then, for expected value of x squared, since this x is a continuous random variable, we take integrals. Since this x is a continuous random variable, take integrals from negative infinity to infinity. Take x squared times f of x dx. And since the support of x is from 0 to 1, Suppose f(x) is the interval from 0 to 1. We take integral from 0 to 1. x squared times f of x. When s is between 0 and 1, f of x is 3x squared. When s is between 0 and 1, f of x is 3x squared. Dx. If we multiply, we get 3x to the power 4 dx. Then take antiderivative. Take antiderivative, we get 3x to the power 5 over 5. Evaluate from 0 to 1. If I plug in 1, I get 3/5. If I plug in 0, I get 0. So expected value of x squared is 3/5. Next, we use the new formula. New formula says variance of x is expected value of x squared minus expected value of x squared. So variance of x is e of x squared minus e of x squared. Then plugging numbers. E of x squared is 3/5 minus e of x. E of x is 3 over 4 square. Then simplify. We have 3/5 minus 9 over 16. Find common denominator, which is 80. 16 times 3 is 48. 5 times 9 is 45. 48 minus 45 is 3 over 80. That's exactly the same as what we have here. Once we know the variance, finding standard deviation is easy. Take square root. That's easy. Once we know the variance, finding the standard deviation is much easier. The hard part is finding the variance. If we use this new formula, usually we have much less computation. If we use the new formula, in general, we have much less computations. And for variance, keep one thing in mind. Variance is always positive. Variance is always greater than or equal to 0. It's always greater than or equal to 0. If you do some computation, you find negative variance, that means you made a mistake. You must go back and check your work. Variance is always greater than or equal to 0. It could be 0, but usually it's positive. Variance of x is usually greater than or equal to 0. If you get some negative number here for variance, that means you made a mistake. You must go back and check your work. Next theorem. Let x be a random variable. Then variance of ax plus b is a squared times variance of x, which means for variance of ax plus b, the constant term disappears. If I pull out coefficient of x, if I pull out a, I must square a. That's this theorem. Now let's prove it. How do we prove it? How do we prove it? Let y, then a random variable y. Then a random variable y equal to ax plus b. Then variance of ax plus b equal to variance of y. What's variance of y? By the previous theorem, variance of y is expected value of y squared minus expected value of y squared. By the previous theorem, variance of x is e of x squared minus e of x squared outside. So first has square inside, second has square outside. First term has square inside, second term has square outside. Then y is as plus b. Here I have as plus b squared minus expected value of ax plus b squared. Now, in the first part here, I can expand the per free square. In the first part here, I can expand the perfect square. If I expand the perfect square, I have a squared x squared plus 2abx plus b squared. For the second part, inside the bracket, e of as plus b, this can be rewritten as a times e of x plus b. Expected value of as plus b can be rewritten as a times e of x plus b. Next, in the first part, I can separate this into three expectations. That is e of a squared x squared plus e of 2abx plus e of b squared. This is a polynomial. I can separate it into three expectations. For the second part, if I expand the perfect square, I have a squared e of x squared. Let me put it here. For the second part, if I expand the perfect square here, I have a squared e of x squared plus 2ab e of x plus b squared. That's the second part. The first part, in the first term here, I can pull out a squared. A squared is a constant. I can pull it outside. I get a squared e of x squared. In the second term, I can pull out 2ab because 2ab are constants. Pull out 2ab, where a and b are constants. So I can pull out 2ab. If I pull out 2ab, I get 2ab e of x. In the third term, b is a constant, so b squared is also constant. Expected value of a constant is the constant itself. Minus the second part here. A squared e of x squared minus 2ab e of x minus b squared. Then 2ab e of x can cancel. Positive negative can cancel. B squared, positive negative b squared can cancel. What's left is a squared e of x squared minus a squared times e of x squared. If I pull out a squared, since a squared is constant, it's a common factor. If I pull out a squared, what's left is, e of x squared minus e of x squared. That's a squared times what? This is what? By the previous theorem, e of x squared minus e of x squared. E of x squared minus e of x squared is variance of x. This is variance of x. So, variance of y equal to a squared times variance of x. And we know the variance of y is the same as variance of as plus b. So, variance of ax plus b equal to a squared times variance of x. Let's complete the proof. This theorem says, if we have variance of as plus b, the constant term disappears. If I pull out a coefficient a, I need to square this number. I get a squared times variance of x. Next, let's look at an example. Let x be a random variable such that e of x is 2 and e of s times s plus 2 is 10. Find the variance of x and the variance of 3x minus 4. Let's find variance of x first. We know that variance of x is e of s squared minus e of x squared. We know e of x already, but we don't know e of x squared. What should we do? Let's find e of x squared first. In order to find the variance of x, let's try to find e of x squared first. So let's try to find e of x squared first. Let's try to use this information here to find e of x squared. We know that e of x times x plus 2 is 10. This is 10. But if I distribute x, what do I get? If I distribute x, what do I get? If I distribute x, I get x squared plus 2x. And then for e of x squared plus 2x, I can separate this. I can write it as e of x squared plus e of 2x. Then I can pull out 2. I get e of x squared plus 2e of x. We know that e of x times x plus 2 is 10. So this is equal to 10. And also we know that e of x is 2. So e of x squared plus 2 times 2 equal to 10. Here 2 times 2 is 4. So e of x squared equal to 10 minus 4, which is 6. Now we know e of x squared. Next we can find variance of x. Variance of x is e of x squared minus e of x squared. E of x squared we just found, that's 6. E of x is 2. E of x is 2. 2 squared is 4. 6 minus 4 is 2. So variance of x is 2. Next, we try to find variance of 3x minus 4. By the previous theorem, variance of 3x minus 4, the constant term disappears. If I pull out the coefficient of x, I need to square this number. So I get 3 squared times variance of x. The constant term disappears. If I pull out coefficient of x, I need to square the coefficient. So I get 3 squared times variance of x. 3 squared is 9. Variance of x we just found, that's 2. 9 times 2 is 18. That's variance of 3x minus 4. Next example, let x be the random variable with x has a binomial distribution with n equal to 3 and p equal to 2/5. And let y be the random variable with y equal to 4x minus 2. Find e of x, variance of x, e of y, variance of y. So first of all, let's find a probability function for x first. Let's find a probability function for x first. Here x has a binomial distribution with n equal to 3, p equal to 2/5. Its probability function is n choose x, p to the power of x times 1 minus p to the power of n minus x. Plugging n and p, n is 3, p is 2/5. We have 3 choose x, 3 choose x, p is 2/5, 2/5 to the power of x times 1 minus p. 1 minus p is 1 minus 2/5, that's 3/5. 3/5 to the power of n minus x, which is 3 minus x. That's the probability function of x. And next, we need to find the support of x. For binomial distribution, support of x is integers from 0 to n. For binomial distribution, support of x is integers from 0 to n. Here n is 3, so we have integers 1, 0, 1, 2, 3. Support of x is integers from 0 to 3. Next, we try to plug in each value in the support into the probability function here. So let's first of all plug in 0. F of 0, I plug in 0 for x. That's 3 to 0. 2/5 to the power of 0. 3/5 to the power of 3. If we multiply, we have 27 over 125. For f of 1, we plug in 1 into the probability function. We get 3 choose 1, 2/5 to the power of 1, 3/5 to the power of 2. Together is 9 times 3 is 27 to the power of 27 times 2 is 54. 54 to the power of 125. Next, f of 2. I plug in 2 into the probability function. I get 3 choose 2. 2/5 to the power of 2. 3/5 to the power of 1. Together we have 9 times 4 is 36 over 25 over 125. Next, for f of 3, we use plug in 3 here. Plug in 3 into the probability function. We get 3 choose 3. 2/5 to the power of 3 times 3/5 to the power of 0. Then we have 2 cubed is a over 125. Next, we try to find e of x. Since x is a discrete random variable, take the sum of all x in the support. X times f of x. Here x in the support is 0, 1, 2, and 3. I have 0 times f of 0, 1 times f of 1, plus 2 times f of 2, plus 3 times f of 3. Then plugging, we have 0 times 27 over 125, plus 1 times 27 over 125, plus 2 times 1 times 54 over 125. One times 54 over 125. Two times f of 2. F of 2 is 36 over 125. Plus 3 times f of 3. F of 3 is a over 125. Together we have 54 plus 72 plus a over 125, which is plus 24. Which is 150 over 125. If I divide top and bottom by 25, I get 6 over 5. That's e of x. Next, let's find e of x squared. Since x is a discrete random variable, take the sum for all x in the support. Find the sum for all x in the support. X squared times f of x. Here, for all x in the support, we have 0, 1, 2, 3. For all x in the support, we have 0, 1, 2, 3. So we have 0 squared times f of 0 plus 1 squared times f of 1 plus 2 squared times f of 2 plus 3 squared times f of 3. Then 0 squared is 0. F of 0 is 27 over 125. 1 squared is 1. F of 1 is 54 over 125. 2 squared is 4. F of 2 is 36 over 125. Three squared is 9. F of 3 is a over 125. Together we have 124 on the bottom. In the numerator, we have 54 plus 144 plus 72. Together, we have 270 over 125. If I divide top and bottom by 5, I have 24 on the bottom and 54 on the top. So that's E of x squared. Next, let's compute variance of x. Variance of x is E of x squared minus E of x squared. We know that E of x squared is 54 over 25. E of x is 6 over 5. Plug in. We have 54 over 25 minus 6 over 5 squared, which is 54 over 25 minus 36 over 25. Subtract 54 over 25 minus 36 over 25 is 18 over 25. That's variance of x. That's variance of x. Next, we try to find E of y and variance of y. Try to find E of y and variance of y. How do we find E of y? What's y? We know that y is 4x minus 2. Y is 4x minus 2. So E of y is the same as E of 4x minus 2. And then for expected value, I can separate this into two expectations. E of 4x plus E of negative 2. And for E of 4x, I can pull out 4. Right, that's 4 times E of x. And expected value of a constant is a constant itself. Expected value of a constant is the constant itself. So I get negative 2. So I have 4 times E of x minus 2. E of x is 6 over 5. So we plug in. I get 4 times 6 over 5 minus 2, which is 24 over 5 minus 2. That's 14 over 5. That's E of y. Next, for variance of y, that's the same as variance of 4s minus 2. Variance of y is variance of 4s minus 2. For variance, the constant term disappears. For variance of 4s minus 2, the constant term disappears. If I pull out a coefficient of 4, if I pull out a coefficient of x, I need to square the coefficient. So for variance of 4s minus 2, constant term disappears. If I pull out a coefficient of x, I need to square the coefficient. So I get 4 squared times variance of x. 4 squared is 16. Variance of x, we just found it here. That's 18 over 25. Then multiply. 16 times 18 is 288. So we get 288 over 25. That's E of y and the variance of y. Next example. Let x be the random variable with PDF f of x, where f of x is 3 over 16 x squared plus 1 over 4x if x is between 0 and 2, and 0 otherwise. And let y be the random variable with y equal to 2x plus 3. Find E of x, variance of x, E of y, variance of y. Let's find E of x first. In order to find E of x, we need to find support of x first. What's support of x? Support of x is the set of all parts of x value. Here x is the value between 0 and 2. if x is given as an interval, for support of x, we must write it as a closed interval from 0 to 2. Support of x, we must write it as a closed interval from 0 to 2. Now, let's find e of x first. Since x is a continuous non-variable, we take integral. Take integral from negative infinity to infinity. Take x times f of x dx. Since x is a continuous non-variable, we take integral. And then here we see that support of x is from 0 to 2. So take integral from 0 to 2. X times f of x. F of x is 3 over 16 times s squared plus 1 over 4x dx. Then distribute x. If I distribute x, I get 3 over 16 s cubed plus 1 over 4 s squared dx. Next, we take antiderivative. We have 3 over 16 times s to the power 4 over 4 plus 1 over 4 times s cubed over 3. Evaluate from 0 to 2. If I plug in 2, 2 to the power 4 is 16. 16 cancel 16 here. I get 3 over 4 in the first term. Second term, if I plug in 2 here, 2 cubed is 8. 8 divided by 2, 8 divided by 4 is 2. So I get 2/3 in the second term. Then if I plug in 0, I get 0. It disappears. Then adding up, 9 plus 8 is 17. I get 17 over 12. That's e of x. Next, we just compute variance of x. In order to find variance of x, we must find e of x squared. Because variance of x is e of x squared minus e of x squared. So in order to find variance of x, we must find e of x. We need to find e of x squared first. Next, let's compute e of x squared. E of x squared. Since x is a continuous non-variable, we take integral from negative infinity to infinity. Then take x squared times f of x dx. Since support of x is from 0 to 2, support of x is the interval from 0 to 2. We take integral from 0 to 2. Take x squared times f of x. Here, when s is between 0 and 2, f of x is 3 over 16 s squared plus 1 over 4x. 3 over 16 s squared plus 1 over 4x dx. Distribute x squared. If I distribute x squared, I have integral from 0 to 2. 3 over 16 s to the power 4 plus 1 over 4 s to the power of 3 dx. Next, I take antiderivative. I get 3 over 16 times x to the power 5 over 5 plus 1 over 4 times x to the power 4 over 4. Evaluate from 0 to 2. If I plug in 2, 2 to the power 5 is 32. 32 divided by 16 is 2. 2 times 3 is 6. So first term is 6 over 5. Second term, if I plug in 2 here, 2 to the power 4 is 16. 16 divided by 4 and 4 is 1. If I plug in 0, I get 0. And 6 over 5 plus 1 is 11 over 5. That's e of x squared. Next, we can find variance of x. Variance of x is e of x squared minus e of x squared. E of x squared we just found, that's 11 over 5. Minus e of x squared. E of x is 17 over 12 squared, which is 11 over 5 minus 289 over 144. Then I use my calculator. I get 139 over 720. That's variance of x. Next, we'll try to find e of y and variance of y. What's e of y? We know that y is 2x plus 3. So e of y is e of 2x plus 3. So I can separate its expression, but it's e of 2x plus e of 3. I can separate its expression. Then I can pull out 2, but it's 2 times e of x. Its derivative of constant. Its derivative of a constant is always a constant itself. So e of 3 is 3. Its derivative of a constant is always a constant itself. So e of 3 is 3. Then I can plug in e of x. E of x is 17 over 12. Plus 3. 2 times 17 over 12 is 17 over 6. Plus 3. That's 35 over 6. That's e of y. Next, for variance of y, y is 2x plus 3. For variance of 2x plus 3, for variance of 2x plus 3, constant term disappear. Constant term disappear. If I try to pull out coefficient of x, I can, when I put it out, I need to square the number. If I pull out 2 here, if I pull out coefficient of x, I need to square 2. I get 2 squared times variance of x. So for variance of 2x plus 3, constant term disappear. If I pull out coefficient of x, I need to square the coefficient. If I pull out 2, I need to square 2. Then we know that 2 squared is 4. Variance of x. Variance of x is 139 over 70. 2 squared is 4. Variance of x is 139 over 720. Then take 4 times 139 over 720. That's 139 over 180. That's the variance of y. Next, let me show you mean and variance of some special probability distributions. Mean and variance of some special probability distributions. Mean is expected value of x, e of x, which is mu. Variance is sigma square. That's mean and variance. Now let me show you mean and variance for some special probability distribution. If x has a binomial distribution with parameters n and p, its mean, e of x, is n times p. Its variance is n times p times 1 minus p. If S is a binomial distribution, e of x is n times p. Variance of x is n times p times 1 minus p. If x has a hypergeometric distribution, with parameters n, n1 and n2, E of x is n times n1 over n1 plus n2, and the variance of x is very long here. That's n times n1 over n1 plus n2 times n2 over n1 plus n2 times n1 plus n2 minus n over n1 plus n2 minus 1. That's the variance of x if x has a hypergeometric distribution. If x has a Poisson distribution, with perimeter lambda, then E of x is lambda. Variance of x is also lambda. If x has a continuous uniform distribution from alpha to beta, if x has a continuous uniform distribution from alpha to beta, then E of x is alpha plus beta over 2. If x has a continuous uniform distribution, E of x is alpha plus beta over 2. Variance of x is beta minus alpha squared over 12. If x has an exponential distribution, if x has an exponential distribution, with perimeter theta, then E of x is theta itself. Variance of x is theta squared. So memorize this theorem, memorize these formulas. At the end of the semester, if we have time, I'll go back and show you the proof for these formulas. Right now, just memorize them. Next, let's look at some examples. First example, when a die is rolled 300 times, let the random variable x represent the number of obtained force. Find E of x and variance of x. First step, we try to recognize what kind of probability distribution x is. So here, when we roll a die, every time the chance of getting 4 is 1 over 6. And we are rolling a die 300 times, means we try the same experiment 300 times. We can think of binomial distribution. So it looks like x has a binomial distribution, where we try the experiment 300 times. That means n equal to 300. The number of trials is 300. The number of trials is 300. And the chance of getting 4 is 1 over 6. That means the chance of getting 4 is 1 over 6. That's P. The chance of getting success is 1 over 6. Then, since x has a binomial distribution, according to the previous formula, we know that expected value of x is np. Variance of x is np, n times t, times 1 minus t. So apply the formula. Apply the formula. Expected value of x is np, which is 300 times 1 over 6, which is 50. Expected value of x is 50. Variance of x is n times p times 1 minus p. N is 300. p is 1 over 6. 1 minus p is 5 over 6. Then multiply. We get 250 over 6, which is 125 over 3. That's the variance of x. Next example. When a real number is randomly chosen on the interval from 0 to 100, let the random variable x represent the value of the chosen number. Find e of x and variance of x. First step, let's decide what kind of probability distribution x is. First step, let's decide what kind of probability distribution x is. Here we randomly choose a number from the interval from 0 to 100, which means every number in the interval has the same chance to be chosen. So this is uniform distribution. And since this is an interval, x is a continuous uniform distribution. So first of all, recognize x is a continuous uniform distribution over an interval from 0 to 100. X is a continuous uniform distribution over an interval from 0 to 100. So here, alpha is 0, beta is 100. That's alpha and beta. Alpha is 0, beta is 100. We try to find expected value of x and variance of x. According to the formula here, for uniform distribution, e of x is alpha plus beta over 2. Variance of x is beta minus alpha squared over 12. So plugging e of x is alpha plus beta over 2, which is 0 plus 100 over 2 is 50. Variance of x is beta minus alpha squared over 12. Here beta is 100, alpha is 0 over 12. 100 squared over 12. That's 10,000 over 12. If I divide top and bottom by 4, I get 2,500 over 3. That's the variance of x. That's e of x. That's variance of x. So using the formula, we can get an answer in a much quicker way. Next example, there are 100 red marbles and 200 blue marbles in a bag. When 50 marbles are randomly chosen from the bag, let the random variable x represent the number of chosen red marbles, and let the random variable y equal to 2x plus 10. Find e of x, variance of x, e of y, and variance of y. So first step, let's recognize what kind of probability distribution x is. Let's first of all recognize what kind of probability distribution x is. In a bag, there are 100 red marbles, 200 blue marbles, and we are randomly choosing 50 marbles from the bag. We can consider there are 100 success, 200 failures. We are choosing 50 marbles, and x represents number of red marbles, so we consider red marble represents success. We consider red marble represents success, and blue marble represents failures. So it looks like hypergeometric distribution. So here x has hypergeometric distribution. With n equal to 50. There are 50 trials. We are choosing 50 marbles from the bag with 50 trials. Since x represents number of red marbles, we consider red marbles represent success. Consider red marble represents success. We have 100 success. And other than red marble, the rest are failures. We have 200 blue marble. Consider we have 200 failures. So x has a hypergeometric distribution. Next, use the formula find mean. Find e of x and variance of x. This is called mean. This is called variance. Use the formula find mean and variance. Find e of x and variance of x. E of x is n times n1 over n1 plus n2. Variance of x is n times n1 over n1 plus n2 times n2 over n1 plus n2 times n1 plus n2 minus n over n1 plus n2 minus 1. So use the formula. E of x is n times n1 over n1 plus n2. N is 50. Plug in n is 50. n1 is 100. n1 plus n2 is 300. 100 over 300 is a third. 50 times a third is 50 over 3. That's E of x. Next, let's find variance of x. The formula for variance of x is very long, but memorize it. That's n times n1 over n1 plus n2 times n2 over n1 plus n2 times n1 plus n2 minus n over n1 plus n2 minus 1. Then plug in n, n1, and n2. I have 50 times n1 is 100, n1 plus n2 is 300, n2 is 200, n1 plus n2 is 300, times n1 plus n2 minus n. 100 plus 200 minus 50 is 250, over n1 plus n2 minus 1. 100 plus 200 minus 1 is 299. Then multiply. That's 50 times 1/3. That's 1/3. That's 2/3. Times 250 over 299. Then multiply numerator to the numerator, denominator to the denominator. On the numerator, 50 times 2 is 100. 100 times 250 is 25,000. That's the numerator. Denominator, 3 times 3 is 9. 9 times 299. 9 times 299 is 2,691. That's variance of x. Next, let's try to compute E of y and variance of y. What's E of y? Here, y is 2x plus 10. So I have E of 2x plus 10. I can separate the expectation, write it as E of 2x plus E of 10. And we know that expected value of 2x, I can pull out 2. Write it as 2 times E of x. And expected value of a constant is the constant itself. If I plug in E of x is 50 over 3 and plus 10. 2 times 50 over 3 plus 10. That's 100. That's 30. 100 plus 30 is 130 over 3. That's E of y. Then for variance of y, that's variance of 2s plus 10. When we have variance of 2s plus 10, if we want to simplify, the constant term disappear. If we try to simplify, the constant term disappear. If I try to pull out a coefficient of x, I need to square the coefficient. So if I pull out 2, I need to square 2. I get 2 squared times variance of x. And here we know that 2 squared is 4. Variance of x is this number, 25,000 over 2,691. When I multiply this number by 4, I get 100,000 over 2,691. That's expected value of y, and that's variance of y. Using the formula, we can get an answer in a much quicker way.